Welcome to a new deep analysis. Today, we're not entering an ordinary topic, we're diving into one of the greatest dilemmas in modern physics. A true mystery. A puzzle that has baffled scientists for decades, and still does. We currently live with two great theories that describe the universe with astonishing accuracy. Yet strangely, they refuse to agree. The first is Einstein's general relativity, the theory that explains gravity, galaxies, stars, and the curvature of spacetime with remarkable precision. The second is quantum mechanics, which governs the world of tiny particles, with its strange rules and counterintuitive behavior. Each theory works perfectly in its own domain. But when we try to combine them, the mathematics collapses. Physics simply stops working. Today, we are drawing on a bold and highly ambitious research paper titled The Unified Fundamental Theory of Quantum Gravitational Spacetime. This paper doesn't merely attempt to fix the problem. No, it proposes something far more radical. It suggests rethinking the foundations from scratch. The paper itself is dense and packed with equations, but our mission today isn't to dive into the math. Our goal is to extract the astonishing core idea at its heart. And that idea can be summarized in a single question? What if space and time are not just an empty stage on which events unfold? What if the stage itself is made of extremely tiny pieces? Like pixels on your smartphone screen. That single idea has the power to change everything. The paper begins with a daring claim. Gravity is not a fundamental force. Instead, it is an emergent phenomenon, arising from the collective behavior of tiny quantum units that make up spacetime itself. Wait, what does emergent mean? Does that mean gravity isn't real? To understand this, let's consider a simple example. Can we say that a single molecule of water is hot? Of course not. Heat only appears when billions of molecules move and vibrate together. It's a collective. According to the paper, gravity works the same way. At the deepest level of reality, there is no gravity. But when countless spacetime pixels interact, the overall effect we experience is what we call gravity. In other words, gravity is a side effect of something far deeper happening in the fabric of reality itself. The paper illustrates this with a powerful visual analogy. Spacetime, which we imagine as smooth and continuous, is like a high-resolution screen. From a distance, the image looks seamless. But zoom in close enough, and you'll see individual pixels. Einstein's spacetime, the paper argues, is simply the view from far away. So what are these pixels made of? And what rules govern them? This is where the first key principle appears. Non-commutative geometry. The term sounds intimidating, but the idea is simple. In our everyday world, if you take one step east and then one step north, you'll reach the same point as if you reverse the order. Order doesn't matter. But at the smallest scale of the universe, order does matter. This implies a fundamental fuzziness in position itself. You can never know everything with absolute precision. And this isn't a limitation of our instruments. It's built into the fabric of reality. This fuzziness defines the smallest meaningful unit of spacetime. The Planck scale. And its importance is enormous, because it solves one of the most dangerous problems in physics. The problem of infinities. In current theories, the center of a black hole is a point of infinite density. A place where the laws of physics break down completely. But in this theory, such a collapse is impossible. You can't compress anything smaller than a single spacetime pixel. No infinities. No breakdown. But does this mean we must throw away Einstein's equations? No. We must evolve them. The paper proposes adding a missing piece to the equations of gravity. The energy and tension of the quantum spacetime fabric itself. The stage is no longer silent. It becomes an actor in the story. This is the true bridge between quantum mechanics and gravity. But mathematical beauty alone is not enough. The crucial question is, can this theory be tested? The answer is yes, at least in principle. The theory predicts tiny deviations in the strength of gravity at extremely small distances. It may leave signatures in the cosmic microwave background, the echo of the Big Bang, or even affect energy levels inside atoms. And here comes a breathtaking idea. The largest force in the universe may leave fingerprints in the smallest physical systems. In the paper's final unification diagram, the full picture emerges. General relativity and the standard model of particle physics. Both arise from a deeper structure, the quantum geometry of spacetime. What we perceive as smooth spacetime is simply the continuous limit of an underlying discrete network. The message is clear. Perhaps we've been looking at the universe the wrong way. Space and time were never just a container for physics. They are the source from which everything else emerges. It's as if this theory is searching for the source code of the universe. And that leaves us with one final, profound question. If the Planck scale is the smallest meaningful unit, what happens if we try to look beyond it? Does the very concept of space collapse? Or does it simply cease to exist? A question we leave open for the physics of the future to answer.